Subtopic 2.2 Quantum Mechanical Model. There are only 3 learning outcomes in this subtopic from A to C. However, learning outcome C will be covered in tutorial classes. Please pause the video and take some time to read the learning outcomes on your own. Let's start with a basic definition and get to know what is atomic orbital. An orbital is a three-dimensional region in space around the nucleus where there is a high probability of finding an electron. Imagine if your nucleus is at the center right here, and in a 3D dimensional region you have this X, Y, and Z axis, and your electron could be here, 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 or even here. So the area or the space in the 3-dimensional region where the probability of finding the electron is what make an orbital. Quantum number. An atomic orbital for hydrogen atom is specified by 4 main quantum numbers. The first one is the principal quantum number, or can be denoted as small letter n. It indicates the energy level of the electron. Second is the angular momentum quantum number, or can be denoted as small letter l. It indicates the shape of the orbital. And the third one is the magnetic quantum number and can be denoted as small letter m. This describes the orientations of the orbital in space. And fourth is the electron spin quantum number, or can be denoted as small letter s. And this small s represents spin directions of electron on its own axis. First quantum number, which is the principal quantum number n. The value of n determines the size and energy of an atomic orbital. The principal quantum number may have only positive integers, the values starting from number 1 followed by 2, 3, and so on up to infinity. You can see that the bigger the number n, the bigger the orbital size, as well as the energy. So what is shown here is an orbital. There are a few types of orbital that we are going to look at on the next slide. What we're seeing right now is what we call as an s orbital. And the orbital size decreases from 3s to 2s to 1s. The value 3, 2, and 1 here is referring to n, which is the principal quantum number. And you can see the differences from 1s, 2s, and 3s. The bigger the value of n, the bigger the orbital size. So the second quantum number is what we call as angular momentum quantum number, which can be denoted as small letter l. It is also called as azimuthal or subsidiary or orbital quantum number. All of this name is referring to angular momentum quantum number. The value of L will be an integer from 0 to n-1. The L will indicate the shape and type of the orbital. The value of n will actually determine the value of L. Let's see this table down here. When your n value is equal to 1, your L is equal to 0. When n is equal to 2, your L value will be 0 and 1. When n is equal to 3, your L value will be 0, 1, and 2. As you can see from here, your L value will always be less than n starting from 0. And from the value of n and L, you can identify your subshell, which is the shape and type of the orbital. So, as your n is equal to 1 and L is equal to 0, your subshell will be 1s orbital. The s referring to the L value, which is if it's 0, it is an s orbital, and the number in front is referring to the value of n, and so on. So, you have 2s here, 2p, 3s for 30, and 3p for 31, and 3d for 32. So take note that, again, the L will identify the orbital shape and type. Okay, so when your L is equal to 0, your type orbital is an s orbital, and the shape is sphere. When your L is equal to 1, your orbital type is p orbital, and the shape is dumbbell. And when your L is equal to 2, your type of orbital is d orbital, and the shape of the orbital is clover leaf. And when your L is equal to 3, your orbital is f orbital, and the shape is much more complex than any of these. So the third quantum number is magnetic quantum number, and it can be denoted as small letter m. The value of m will be an integer from negative L through 0 to positive L, or simply remember m is equal to negative L, 0 plus L. The m indicates the orientations of the orbital in the space around the nucleus. The value of m depends on the value of L. So for example, when L is equal to 0, your m will be equal to 0. So you only have one possible s orbital with one orientation. When L is equal to 1, then your m value will be negative 1, 0, plus 1. That means you have 3 possible p orbitals with 3 different orientations. When L is equal to 2, you have m value is equal to negative 2, negative 1, 0, plus 1, and plus 2. This means that you have 5 possible d orbital with 5 different orientations. The fourth and the last quantum number is electron spin quantum number, and it can be denoted as small letter s. The s determines the direction of spinning motions of an electron. There are only two possible motions of an electron, either clockwise or anti-clockwise, and the value of s is equal to positive half referring to clockwise and negative half referring to anti-clockwise motions. By now, we have been introduced to all of the 4 quantum numbers, and each allowed combinations of those n, l, and m values can specify one atomic orbital or can tell you what kind of orbital it is in terms of its size, shape, and spatial orientation. So let's take a look at this table below. So this value n, l, and m, it can tell you what are the orbitals name or type, how many number of orbital that exist, and how many number of electron that can occupy in the orbital. So when n is equal to 1, l is equal to 0, m also 0, so the orbital name or type for this orbital is 1s orbital because of this value. And the number of orbital, how many number of orbital that exist? 1, because it only has one orientation. And number of electron that it can occupy in this orbital is 2, because each orbital can occupy 2 electron maximum. And for n equal to 2, l can be 0, so m also 0, and the orbital name is 2s, and the number of orbital is also 1 because one orientation. And number of electron that can occupy in that one orbital is 2. When n is equal to 2, l can also equal to 1. m equal to negative 1, 0, positive 1. So the orbital name is now become 2p because this value, okay? And then the number of orbital is 3 because you have 3 orientation, and the number of electron that occupy in this orbital is 3 times 2, 6. Alright? And when n is equal to 3, l is equal to 0, m equal to 0. Orbital name 3s. Number of orbital 1, number of electron 2. When n equal to 3, l also equal to 1. So m equal to negative 1, 0, plus 1. Orbital name 3p. Number of orbital will be 3. And the number of electron 3 times 2 is 6. And when n equal to 3, l also equal to 2. So m is equal to negative 2, negative 1, 0, plus 1, plus 2. Orbital name is 3d. So by now, you must know how many number of orbital that exist. It is 5 orbitals. And the number of electron that can occupy in the orbital is 10 because you have 5 orbitals. So before we further continue our lesson, there is some point worth to remember. It is the relationship between the n, l, and m quantum numbers. The values of n will limit the values of l, and the values of l will limit the values of m. For example, if we have n is equal to 2, the possible l values will be 0 and 1. Okay? So when l is equal to 1, the possible m values would be then negative 1, 0, plus 1. And when l is equal to 0, the possible m values is only 0. So the total number of orbital is 4, and the total maximum electron that can occupy in this 4 orbital is 8 electron. Or you can use this formula to find the maximum number of electrons that can occupy in the orbital, which is equal to 2 multiplied by n squared, and you will get the same answer as 8 electrons. The shape of s orbital is sphere. From this diagram shown here, you can see the size of s orbital with different values of n. And the size for 1s orbital is smallest compared to 3s orbital. So the bigger the value of n, the bigger the size, and also the bigger the energy. For p orbital, it is represented by L is equal to 1 value, and each p orbital has dumbbell shape and separated by a node at the nucleus. The L is equal to 1, that means there are 3 possible values for m, which is m is equal to negative 1, 0, and plus 1, which then refer to 3p orbital, px, py, and pz. As m increases, the p orbital also get larger. So you can see 3 different orientations of p orbital, px, py, and pz. So the shape of the p orbital is like a dumbbell. So as for d orbital, it is represented by the value of L equal to 2, and all of the d orbitals do not look alike. There are 5 possible m values for L equal to 2, which are negative 2, negative 1, 0, plus 1, and plus 2, which then correspond to 5 d orbital with 5 different orientation, and the orientations are d exact, dyz orbital, dxz orbital, dx squared y squared, and dz squared orbital. So the shape of d orbital will look like this. You can try and practice to draw on your own. Let's go through some example. Example 10. The question asks you to specify the L and M values for n equal to 4. So when n equal to 4, the possible L value will be 0, 1, 2, 3. And for the M, you can make a table like this to organize the answer. When L equal to 0, the M will be 0. When L equal to 1, M will be -1 to +1. When L equal to 2, the M will be -1 to +2. And when L equal to 3, the possible values for M will be -3 to +3. So next example, this example 11 asks you to give all possible M values for orbitals that have each of the following, which are for A, L equal to 2. So when L equal to 2, the possible values for M is -2 to +2. And when N equal to 4, L equal to 3, the possible M values will be -3 to +3. So that's it. So example 12. The questions ask you to give name, magnetic quantum numbers, and numbers of orbitals for each subset with the following quantum numbers. Since the question asks you to many things, you can make a table like this to make it more organized and easy to answer. So for part A, the condition given is n equal to 3, L equal to 2. So the name of orbital will be 3D. As the condition strict to L only equal to 2, so the possible m values will be -2 to +2. And the number of orbital is 5 orbitals. And for part B, the condition given is n equal to 2, L equal to 0, strict to 0. So the name of orbital is 2s. And the possible m value is only 0. So the number of orbitals only 1. And for part C, n is equal to 5, L equal to 1. So name of orbital is 5p. So the possible m values according to L equal to 1 is only -1 to +1. And the number of orbital is 3. And lastly, part D, the condition given is n equal to 4, L equal to 3. So the name of orbital will be 4f, and the possible m values will be -3 to +3. And total number of orbitals is 7. Example 13. The questions ask whether the following quantum number combinations are allowed or not. If it's not, you have to show 2 ways to correct them. So let's see the first part of this example. For part A, the combinations given are n equal to 1, L equal to 0, and M equal to -1. In order for you to check whether this is allowed or not, you have to try and work it out first. When n is equal to 1, you know that L must be equal to 0. So the given value L equal to 0 is correct. So let's check the given value for M whether it is correct or not. So when L is equal to 0, M must also be equal to 0. So the value given of M equal to -1 is incorrect. Therefore, you know that the combination is not allowed. So you have to show 2 ways to correct them. Remember, the value of N limit the number or the value of L, and the value of L will limit the value of M. And the first way to correct is, since the value of M here is incorrect for the combination to be allowed, you can give the right value for M for the combination to be allowed. So when M is equal to 1, L is equal to 0, M must be equal to 0 for the combination to be allowed. And the other way to correct this combination is word by word and remain the value of M but change the value of L and change the value of N if it's needed. Since we remain the value of M equal to -1, L must be equal to any number that will have the possible value of M equal to -1. In this case, I have chosen L equal to 1. And since L is equal to 1, N must be any number bigger than 1. Therefore, I have chosen N is equal to 2. So this is the second way to correct the combination. So let's see at the combination. For part B, the combinations given is N equal to 4, L equal to 3, and M equal to -1. To check whether this combination is allowed or not, we have to again try to work it out first. So you know that when N equal to 4, L must be 0, 1, 2, and 3. So that means this value of L equal to 3 is correct. And let's check for value of M here. So we know that when L equals to 3, the values for M must be from -3 to +3. So this -1 value is included within the range. That means this value is also correct. So all of this combination is allowed. So no corrections are needed. So let's see the last example for this particular question. So for part C, the combination given is N equal to 5, L equal to 2, and M equal to +3. Again, same thing, we need to try and work it out to check whether this combination is allowed or not. So you know that when N is equal to 5, L must be equal to 0, 1, 2, 3, 4 only. So the given value of L equal to 2 is correct because it's within this range. So let's check for value of m whether this is correct or not. So you know that when L is equal to 2, m values must be from -2 to +2 only. So the given value of m equal to +3 is incorrect because it is out of this range. That means you know that the combination is not allowed. So you have to propose two ways of solution to correct the combinations. So remember, recall that L limit the value of m. So what you can do is, first you have to give the correct value for m since m is incorrect. So when m is equal to 5, L is equal to 2. So the correct value for m in this case is m must be equal to any number from this range, -2 to +2. If you choose any number from this value, you are correct. In this case, I've chosen +2. And the other way is, since you know that L value limit m, you can actually change the value of L instead of m. So when m equal to 5, L must be equal to 3 for m to be equal to +3. So, example 14. The questions asks, for the following subshells, give the values of the quantum numbers n, l, m, and the number of orbitals in each subcell. Before we continue, let's recall the value of L. If it's 0, 1, 2, and 3, what are the type of orbital it is referring to? So, 0 is S, and then we have P, S, P, D, and F orbital. So, it will be easier for you to answer this example. So, let's try to answer it. For the first part, the subshell given is 3P. So, the value of n must be equal to 3, referring to the value given here. And L must be equal to 1, referring to the letter here. P equal to L equal to 1. And since L is equal to 1, m must be -1 to +1. So the value of m referring to value of L. And the number of orbitals is 3 orbitals. So number of orbital determined by the orientation number. And let's move on to part B. Part B, the subshell given is 5D. So the value of n must be equal to 5, L must be equal to 2, and therefore m must be equal to range from -2 to +2. So the total number of orbitals are 5 orbitals. And lastly, part C, the given subshell is 4F. So you know that the n must be equal to 4, L equal to 3, m equal to range -3 to +3. So the total number of orbitals are 7 orbitals. So that's it for now.